Hi, welcome to the video lecture on parallel resonance part 2. In the previous video, that is parallel resonance part 1, we would have seen about the resonant frequency of parallel RLC circuit. So in this video, we are going to see about the quality factor of parallel RLC circuit, next the bandwidth of parallel RLC circuit, and finally the selectivity of parallel RLC circuit. First, we'll see the Q factor or the quality factor of a parallel RLC circuit. Q factor is defined as the maximum energy stored to the energy dissipated in one period. The term 2 pi is introduced to simplify the expression for quality factor. So the quality factor at resonance, that is QR, is equal to the same expression. Along with that, you have to use the term at resonance. Okay, so this is the formula for calculating this quality factor. Now, by deriving, we get the QR is equal to omega R CR. So we already know what is omega R, that is angular resonant frequency, which is equal to 1 by root of LC. From this, get the expression of C. So the quality factor at resonance can also be expressed as shown below, that is QR is equal to R by omega R into L. This can be got by substituting the expression for C, which you have got here. It can also be represented as R into root of C by L. This expression can be derived by replacing this omega R by 1 by root of LC. So when the condition is for frequencies less than the resonant frequency, Q is equal to R by omega L, that is RLC parallel circuit behaves as an inductive circuit. And for the condition when omega, which is greater than or equal to omega R, that is frequency is higher than the resonant frequency, your Q value is going to be omega CR, that is the RLC parallel circuit behaves as a capacitive circuit. Okay, so next we are moving on to bandwidth. Now look at this graph carefully. You can see this omega R, that is resonant frequency, and omega L, that is lower cutoff frequency, and omega H, that is higher cutoff frequency. So the definition for lower cutoff frequency is when the frequency is decreased from the resonant value, we come across a frequency at which the power is twice the minimum value or the current is root 2 times the minimum value, and this frequency is called lower cutoff frequency. The same way you can define higher cutoff frequency, that is when the frequency is increased from the resonant value, we come across a frequency at which the power is twice the minimum value or current is root 2 times the minimum value, then that frequency is called as higher cutoff frequency. So the bandwidth is defined as the difference between the higher cutoff frequency and lower cutoff frequency. So it's denoted by the term beta, and the unit of bandwidth is radians per second or hertz. So by derivation, you get this higher cutoff angular frequency omega H and lower cutoff angular frequency omega L. So first two equations are derived, and finally you can write in alternative equations of 3 and 4 in terms of this quality factor. Okay, so if you want to express in terms of hertz, just divide it by 2 pi. So finally beta is equal to 1 by RC in radians per second. If you want to express in hertz, just divide it by 2 pi. So it's 1 by 2 pi into RC in hertz. If you want to express this beta in terms of quality factor, it is going to be omega R divided by QR in radians per second. Okay, so finally we are moving on to the selectivity of the parallel RLC circuit. Now look at this graph, that is under resonance condition, the voltage response, okay, in an RLC parallel circuit will have this kind of selectivity, that it selects a particular frequency and rejects all the other frequency. So selectivity is defined as the ratio of bandwidth and resonant frequency. So you know already what is bandwidth, that is omega H minus omega L divided by omega R. So finally you look at this portion, that is from this we can say that the circuit is highly selective. That is the value of selectivity is low, which is possible with a smaller value of bandwidth, beta. So selectivity is inverse with that of the quality factor. So you know already what is beta, right? It is going to be omega R by QR. So from this you can also write selectivity is equal to beta by omega R. So it's going to be 1 by QR. So when the Q factor is high, selectivity will definitely be small, and so the circuit is highly selective. So I hope by watching this video, you would have clearly understood about the quality factor, bandwidth, and selectivity of parallel RLC circuits. So thanks for watching.